course of digital signal processing. Today we will start lecture number 10, chapter number 3, that is ZTransform. In this chapter we will talk about the ZTransform, inverse ZTransform, properties of ZTransform, and what kind of analysis we can do with the help of ZTransform. So let's get started. As we know that Fourier transform plays an important role in analyzing discrete time signals and system. In this chapter we will talk about the Z-transform of signals and system and also discuss the properties of sequence related to the properties of Z-transform. Z-transform is basically the counterpart of Laplace transform. Z-transform is basically for discrete time signals and system, whereas Laplace transform is for continuous time signals and system. Both are generalization of Fourier transform. The generalization of continuous Fourier transform is Laplace transform, whereas the generalization of discrete time Fourier transform is Z-transform. The reason for introducing these generalization, that is Laplace and Z-transform, is that Fourier transform does not converge for all these sequences. So it is useful to use the generalization. So with the help of Z or with the help of S, we can make the signal to converge. So let's get started with Z-transform. So as you can see in equation 3.1, which is the equation of Fourier transform of signal x of n, x e raised power j omega is equal to summation x of n e raised power minus j omega n. This is the formulation that we use to find out the Fourier transform of discrete time signal. So if I extend this to Z-transform, the Z-transform of the sequence x of n, so the same sequence x of n will have a Z-transform x of z is equal to summation minus infinity to infinity x of n z raised power minus n. Now if you compare 3.1 and 3.2 equation, you will see that z is a complex variable and z is equal to e raised power j omega. So now z has two values, z has phase and z have magnitude, because e raised power j omega is in polar form. So z is a complex variable which has some magnitude and which has some phase. So let's move on to next slide and discuss some more points about Z-transform. So if you look at equation 3.3, the equation in general is an infinite sum of power series. Why we are calling it power series? Because n starts from minus infinity and goes towards infinity. So z will have value z minus infinity, z0, 1, 2, 3 up to z infinity. So z is an operator that basically maps discrete time signal to Z-transform. Okay, so you can see that z is an operator. This is an operator that is mapping this discrete time signal into Z-transform. Okay, so z is a function or transformation. Now you can see that x of n and then mapping towards x of z. With this interpretation, the Z-transform operator is seen to transform the sequence. So z transform the sequence x of n to x of z. And as I've told you, z is basically a complex variable and it's a continuous variable because z is equal to r e raised power minus j omega. This is continuous because of this omega. So z is a continuous complex variable, and this is the correspondence between discrete time signal and Z-transform. Now Z-transform can be defined in two ways. Either the Z-transform will be two-sided or bilateral, and in contrast to one-sided or unilateral Z-transform. So this equation, if you look at this equation is of unilateral Z-transform because it starts from 0 and goes towards infinity. So it is for only one side. Bilateral and unilateral transform are equal only if x of n is equal to 0 for n less than 0. So both the transform will be equal if signal is 0 for n less than 0. Now if you look at equation 3.3, this is a bilateral or two-sided because both the sides are involved, negative values and positive values. So this is a unilateral bilateral Z transform, and this is a unilateral Z transform. Unilateral and bilateral are equal only if the signal is 0 for n less than 0. If if signal is defined for both positive and negative values, it is bilateral. Let's move on to next slide. As I've told you in previous slide that there is a close relationship between the Z transform and the Fourier transform. So Z transform is basically a complex variable which has, this is magnitude R and this is phase omega. Okay, so Z transform is basically equal to, because if you remember we have Z is equal to e raised power minus j omega. If you look at equation 3.1 and 3.2, if you compare them, so Z transform and Fourier transform are equal when the value of this R is 1. R is equal to 1 means that magnitude of Z is equal to 1. Okay, so both are equal when R is equal to 1, which we can prove here. We know that the Fourier transform formula is x e raised power j omega. We are choosing R here, summation minus infinity to infinity signal, and then R e raised power j omega minus n. So we have just placed the value of Z to be R e raised power j omega in equation 3.2. Now if I just realign them, and I can see x of n R raised to power minus n, and then this is the term that is left for the Fourier transform. So we can see that this equation is equal to Fourier transform if and only if this R is 1 and this R is 1. So if R is equal to 1, then obviously this equation reduces to Fourier transform, because Fourier transform equation is x e raised to power j omega summation x of n e raised to power minus j omega. So we can say that Fourier transform and Z transform are equal when the magnitude of Z is 1 or the value of R is 1. Okay, so the takeaway point is that if Z has a unity magnitude, the Z transform will be equal to Fourier transform. Obviously Z is a complex variable in polar domain. This is in polar domain or polar form. This is the magnitude and this is the phase. Now as we know that Z is a complex variable, it is convenient to describe and interpret it using a complex Z-plane. So this is our complex Z-plane. It has real axis and imaginary axis. And then to define the relationship between Z transform and Fourier transform, we have a unit circle. So this is a circle of radius unit. Okay, so this is a unit circle with a radius of 1, and this is the value of Z. This value of Z can lie anywhere in this Z plane. Okay, this value of Z can lie anywhere in the Z. For example, if this value is here, if this value is right on the unit circle, it means the magnitude of R is, magnitude of Z is 1. Okay, and omega is the angle that this vector Z makes with the real axis. Okay, this omega is the angle which this vector Z makes with the real axis. Okay, so if we calculate Z transform anywhere on this circle, it will be equal to the Fourier transform. As you can see here, this contour is referred to as the unit circle. The Z transform evaluated on the unit circle correspond to the Fourier transform. Omega is the angle between vector to a point Z on the unit circle on the real axis. So there are two things to remember here. If you remember from chapter 2, we know that Fourier transform does not converge for all the sequences. Infinite sum may not always be finite. Similarly, Z-transform does not converge for all the values of Z. So what we have to do, we have to find the values of Z. In Z-transform, our goal is to find the values of Z for which Z-transform converges. And we call it region of convergence. We call it ROC, region of convergence. Okay. So we have to find out the values of Z for which the sequence is absolutely summable and converges to a continuous function of omega. So we have to make sure that this power series, this is power series. Why we are calling this power series? Because of this r raised to power minus n. This should be less than infinity. Okay. So we have to find out the values of Z for which the sequence converges. Okay. For example, we have a sequence x of n is equal to u of n. Now if I cannot find the Fourier transform because this is not absolutely summable, and therefore the Fourier transform does not converge absolutely. However, if I have like r raised to power minus f, u of n is absolutely summable if r is greater than 1. So what we are doing here, we are introducing a variable z. With the help of z variables, we can make the sequence to converge. For example, this x of n is equal to u of n does not converge, or is not absolutely summable, because it is u of n is 1 1 1 and it doesn't go away till infinity. But what if we just multiply r raised to power minus n? So if this x of n is u of n and then it is multiplied by r raised to power minus 1, we can choose the value of r such that this sequence become decreasing. So once the sequence become decreasing, it will be absolutely summable. This means that Z transform for unit step exists with the region of convergence Z greater than 1. So let's move on to the next slide, and I will clarify why we are calling Z greater than 1 to be the region of convergence. So this is how the region of convergence looks like. You can see here the shaded region. So the region of convergence ROC is a ring in the Z plane. So the region of convergence will always be in the form of ring. It can be between these two rings, it can be beyond this side, or it can be this. So region of convergence is always a ring in the Z plane. Okay. So for specific cases, the inner boundary can extend inward to the origin. So this can be the region of convergence. Okay. The ROC becomes a disk. This can be the region of convergence. So overlapping of these two, or this can be the region of convergence. Why we are saying this region of convergence? I can take the values of Z which are greater than this circle. I can take the values of Z which are between these two circles, or I can take the values of Z which are inside this circle only. Okay, so this is region of convergence. Let's move on to the next slide. So the function of Z transform will be a rational function. X of Z is equal to P of Z divided by Q of Z. It will be in the form of P of Z and Q of Z. We will have polynomials in numerators and we will have polynomials in denominators. So the values of Z for which this function X of Z is equal to 0 are called zeros of X of Z. And the values of Z for which X of Z is infinite, it means that Q of Z is equal to 0, are referred to as poles. So when X of Z is equal to 0, we call them zeros. When X of Z is equal to infinite, we call them poles. The poles of X of Z for finite values of Z are the roots of denominators. So poles are basically the roots of denominator and zeros are the roots of numerator. Pole may occur at 0 or infinity other than other values of Z. Okay, so let's move on to next slide. So this is our first example of right-sided exponential sequence. You must need to understand that for this particular type of signals, we will have a region of convergence that is always fixed. So the right-sided signal is defined by u of n. U of n is defined for only right side, and then we have a raised to n, which is multiplied with this to make this function exponential. Because it is non-zero only for n greater than equal to 0. This example is of right side. So using the formula of ZTransform, we know that x of z is equal to summation minus infinity to infinity x of n. So x of n is this signal. So a raised power n, u of n, z raised power minus n. Then we can remove this u of n and change the limit from 0 to infinity, because this u of n defined from 0 to infinity. And then we can take the power n common. So now for this summation to exist, the Z transform will converge if and only if the sum is less than infinity. Okay, if sum is less than infinity, and we know that this summation will be less than infinity when this argument is less than 1, because if something is less than 1 raised power n and that n is increasing, for example if I have 0.5 raised to power n, so the value of n will increase 0 plus 0.5 plus 0.5 raised to power 2. So as long as power is increasing, the sequence will die down, because this will be 1 plus 0.5 plus 0.25 and so on. So we need to have this argument to be less than 1. We want this to be less than 1. So I can say a z raised to power minus 1 should be less than 1. Or I can say a divided by z mod should be less than 1. Or a mod should be less than z mod. Or z mod should be greater than a mod. It means that whatever the value of a is, I will always take z to be greater than a. This is the region of convergence. This is the region of convergence. I have found that this signal will converge whenever the value of z is greater than a. So we can check that if the value of a is, let's say 2, if the value of a is equal to 2 and I take z is equal to 3, okay, or I can take z is equal to 2.1. So 2 multiplied by 1 by 3 raised to power n. If I solve this, this will become 0.6 raised to power n. So this value is less than 1. Anything less than 1 raised to power n, this sequence will converge. This sequence will converge. Okay. So we have the condition z mod greater than a mod. So now we are solving it for the values of zeros and poles. So we know that this is a finite length geometric series. So in order to open this, first term will be a z raised to power 0. So this is first term. 1 minus our ratio. So ratio is a z inverse. Okay. So if you simplify it, 1 divided by 1 minus a z inverse, this is your pole value. Or we can simply simplify it, a divided by z, z minus a divided by z, or z divided by z minus a. Now if I put z is equal to 0, this is our 0. Because if I put z is equal to 0, function x of z becomes 0. And if I put z is equal to a, x of z become infinity, because a divided by 0 is infinity. So this is 0 and this is pole. Okay. So here they have taken the value of a to be 1. So if I take the value of a to be 1, this is our function. 1 divided by 1 minus z inverse. Okay, or I can have the function z divided by z minus 1. So they have just used this equation and written this here and have taken the value of z to be a to be 1. So as per our condition, z mod should be greater than a mod. So z mod should be greater than 1. So this is the region of convergence. So I can take all the values of z that are greater than 1 and the sequence will converge. Let's move on to next slide and see the region of convergence. So before moving on to the region of convergence, we will have a Z-plane and we will have a pole zero plot. So in pole zero plot, we represent 0 with this hollow circle and we represent poles with this cross. Okay, we know that we have a 0 at z is equal to 0 and we have a pole at z is equal to 1, because when we put z is equal to a, the function becomes infinite, and when we put z is equal to 0, the function becomes 0. And our region of convergence is z mod greater than a mod. As long as we have this region of convergence and our values of z are greater than a mod, the sequence will converge and the value of a is 1. So I can take any value of z that is greater than 1, our sequence will converge. Let's move on to next slide and finally see this out. So this is the pole zero plot and the region of convergence. So this is a unit circle, the borderline. This is our imaginary axis, real axis, and then we have a 0 at the origin. This is a 0 at the origin, and then we have a, the value of a that they have chosen here is point, let's say 5. So this is 1, this is 0.5, or we can say that this is 0.7. So if the value of a is 0.5, you can see that we can choose any value that is greater than this. So the sequence will converge. So the value of a is 0.5, so I can take the values of z that are greater than 0.5. So you can see we have a pole at 0.5 on the real axis. The pole is on real axis at 0.5, and we can take any values outside this circle, outside this dotted circle. So the sequence will converge. Thank you.